This video covers rotational kinematics. Our next couple of units are going to focus on rotation. Now it's going to feel like we're going back to the very beginning because we are going to start with kinematics. If you look at this circle, at different points you have different velocities, not just because you're changing direction at each of these points, but because you're actually traveling a different speed at each of these points. Now, all points the same distance from the axis, which is the center in this case, are going to have the same speed, but again have different directions. The best way to picture this is to imagine a gate with A, B, C, and D located along this gate. Now, if you swing this gate open, the time required to move the distances shown here in red is the same for all 4 points. However, points more distant from the axis must travel farther. So again, you can see that these distances are increasing as you move away from the center of the circle. These points must have a greater speed. But all points on a rotating system move through the same angle in a time t. So it helps if we change the way that we're going to be looking at these quantities that analyze motion for things that rotate. Now the first one we're going to look at is angular displacement. Theta naught is going to represent our initial angle, and theta is going to represent our final angle. So a delta theta is going to represent a change in angles. So here, all angular quantities are going to be in radians, but you don't have to change the mode on your calculator. Now, if you know your angular displacement, delta theta, and you know the radius of your circle, then you can calculate x, which is your tangential displacement. What that means is you can use it to calculate this outer portion of your circle, this distance traveled. So you can think of a full rotation on a bike. If you were to cut that circle open and lay it out flat, then the distance would be from here to, let's say, about here. Now, again, that is x, our distance traveled in the x direction, or in this case, tangential displacement. Now we said that all of our quantities are going to be in radians, but most of our information is usually given in degrees or revolutions. So these are going to be some important conversions. If you have an angle in degrees, then you can multiply it by pi over 180 degrees to get your radians. So pi over 3 would be 60 degrees in radians. Also, another important conversion is 1 revolution. Again, 1 complete turn around our circle, or 2 pi radians, or 360 degrees. Now another quantity we're going to look at is angular velocity. Since velocity is defined as the rate of change of displacement, angular velocity, which is represented by an omega, is defined as the rate of change of angular displacement. So just like we saw in translational velocity, we're going to have average and instantaneous quantities. So for average angular velocity, we have our change in angular displacement over change in time. And the instantaneous angular velocity will be the derivative of your angular position with respect to time. So a little bit more about direction. Now, we know that the velocity is changing direction at every single point, so we need to come up with a new way to figure out our direction. Now, this is our first right-hand rule for this semester. Our fingers are going to curl in the direction that it is rotating. So normally we use the phrases clockwise and counterclockwise. So represented by CW or CCW. Now, clockwise is actually going to be considered negative or into the page, like this example here. And counterclockwise is going to be considered positive or coming out of the page here. Now, when we say going into the page or coming out of the page, it's usually you're reading a problem and the direction of the right-hand rule is going to tell you whether it's coming out or in. Again, your fingers are going to be curling in the direction of the rotation, and the direction that your thumb points is going to tell you the direction of your angular velocity vector. Now, just like in translational motion, if your angular velocity and what we're going to see in a little bit, your angular acceleration, are in the same direction, then it's going to be speeding up. So a speed up in rotation. If they're going in opposite directions, then that means that your rotations are going to be slowing down. Like I mentioned, we're also going to have average angular acceleration, which is going to be represented by an alpha. Now, average angular acceleration is our change in angular velocity with respect to time, and our instantaneous angular acceleration will be the derivative of angular velocity with respect to time. Now, because we do have our instantaneous quantities, we can also rewrite these as integrals, which are located down here. Now, just like before, how we had an equation to go from angular displacement to translational displacement, then we can also go from our angular velocity to our translational velocity. In this case, because it is a velocity as we move around the circle, this is also known as our tangential velocity or tangential speed, like we saw in the centripetal acceleration equations. And finally, if we have a angular acceleration, then we can also calculate our tangential acceleration. Again, this equation is for when you are not moving in a uniform, constant motion around the circle, that you are actually speeding up as we move in rotation or slowing down. Now, you can see that all of this was eventually leading up to rotational kinematic equations. Again, everything like we've seen before, our velocities are going to be angular velocities, our displacements will be angular displacements, and our angular accelerations are going to represent our tangential accelerations. So all of the equations can be rewritten in angular quantities, but here I'm only showing the big three. Now, just like in our regular kinematic equations, these equations can only be used for constant angular accelerations. Now, our last slide mentioned tangential acceleration. It's important to realize that there is a difference between tangential acceleration and centripetal, or also known as radial acceleration. Now, tangential acceleration happens when you are speeding up as you move in a circle. Centripetal acceleration is when these changes in velocity actually cause an acceleration towards the center of your circle. So again, these are two very different accelerations and they point in different directions. Tangential, again, will be tangent to our circle, and centripetal will always be towards the center. Now, we can actually calculate, because both of these are vectors, our overall resultant acceleration, which you can guess is the Pythagorean theorem of these two values. Now for a few examples. An object rotates with a constant angular speed. Just like in kinematics, constant angular speeds tells us that we're going to have zero angular acceleration. It completes 10 revolutions in 2 seconds. So this is giving you your angular speed in a way. Determine each of the following for a point P that is 4 meters from the axis. So again, 10 revolutions in 2 seconds, we need all of our quantities to be in radians. So 10 revolutions times 2 pi radians over 1 revolution, again, this is simply a conversion, tells us that our angular displacement is 62.8 radians. The second part is asking for tangential displacement. Again, if you know your angular displacement and you multiply it by your radius, then we can calculate our tangential displacement. In this case, 251 meters. If you're asked to calculate your angular velocity, here our constant angular speed is going to be just our angular displacement divided by time. So 31.4 radians per second. Now tangential velocity, again, if you know your angular velocity, then you can calculate your tangential velocity. In this case, 126 meters per second. So for E, F, and G, we know that our angular acceleration is 0 because we're moving at a constant angular speed. So if we have 0 angular acceleration, we also have 0 tangential acceleration. But now we can double check our radial acceleration or centripetal acceleration, which is simply v squared over r. Our velocity, like it was in the previous slide, 126 meters per second squared divided by r gives us 3,950 meters per second squared. So again, we can still have centripetal acceleration even though we don't have tangential acceleration. So just to show you an example of the rotational kinematic equations, an object initially at rest rotates with an angular acceleration of 6 radians per second squared. How many revolutions has the object completed when it reaches a point where it is spinning at 120 rotations per minute? Now, again, it does tell us that we began at rest, so our initial angular speed is 0. Our final angular speed is going to come from this 120 revolutions per minute, but again, omega is in radians per second. So that means we need to convert this 120 revolutions or rotations per minute into radians per second. So again, one revolution is 2 pi. 1 minute is 60 seconds. So that gives us a 12.6 radians per second final angular velocity. So I'm not really told anything about the direction of any of these values, so we can assume that they're going in the counterclockwise direction or positive. Now it does give us an angular acceleration of 6 radians per second squared. And we're asked to calculate how many revolutions this object has completed when it reaches this final speed. So we're trying to solve for delta theta. So we don't need time in this case. So the only equation that has all 4 pieces without time included is omega squared equals omega naught squared plus 2 alpha delta theta. So here we're trying to solve for delta theta. So this becomes omega squared, and I can cancel out the omega naught because it began at 0, divided by 2 times our alpha. So this is 12.6 radians per second squared, divided by 2 times our angular acceleration, which is 6 radians per second squared, which gives us a value of 13.2 radians. Now the problem did ask us to convert back to revolutions, so now that we have these 13.2 radians, then we need to convert back. So 2 pi radians gives us 1 revolution. So these radians are going to cancel out and we get 2.09 revolutions. 2.1 is okay here too.